doing the solving, by the way, this is second degree homogeneous recursive solving. That's what this is called. It's second degree because we have two recursive terms in it equal to a of n. That's why it's second degree. And because it's second degree, we can turn it into quadratics and solve with it. So that's why we're able to do this. This one is going to have a complex, and I'm going to show you how to deal with it. It's going to be a little ugly, but you're going to be fine. First thing, put everything on one side. All right, so no problem. Lambda squared plus 2 lambda plus 1? No. 2, yeah, because 1 would factor. 2 will not. Okay, then we do our little quadratic formula. So lambda is equal to negative 2 plus or minus square root 2 squared minus 4 times 2 times 1 all over 2 times 1, which is negative 2 plus or minus the square root of negative 4 over 2, which is negative 2 over 2 plus or minus square root of 4 times the square root of negative 1 over 2. Do you see where I get negative 1 plus or minus I? Is that all right? Those are your two lambdas, so I'm going to write those up here. Lambda 1 is negative 1 plus I. Lambda 2 is negative 1 minus I. For complex, you're going to have your A of n formula that looks like this. C1 times x plus yi to the n plus C2 x plus yi to the n. And if you look at this, doesn't this look exactly like my last one, except this is lambda 1 and this is lambda 2? It's still the same thing. It's nothing super nasty. Now, the problem is going to be when we want to find C1 and C2. But we're going to do it. We're going to do it. We're going to do this. Okay? So the first one was A0. Tell me what A0 was again. Was it 2? Okay. And then what was A1? Negative 2. Okay. So here goes. So we have A0, and n, of course, is 0. Here, n is equal to 1. And I'm going to say that 2 is equal to C1 times blah to the 0 plus C2 blah blah to the 0. So you can see how this is 2 is equal to C1 plus C2. Can you write this with me? Or you've got it already? Awesome. Okay, now I can tell you this, and you can believe me, or you can say, Dr. Sauer, prove it. C1 and C2 are just going to be half of this every time. You want to see it proven? Yeah, I'll prove it for you. I couldn't third hour, but on my prep I figured it out. So I'm going to do it. For this next one, we're going to have negative 2 is equal to C1 times negative 1 plus I to the first plus C2 times negative 1 minus I to the first. And don't forget that C2 is 2 minus C1, right? Don't forget that. It comes from here. So we'll have negative 2 equals C1 times negative 1 plus I plus 2 minus C1 times negative 1 minus I. For all those out there in computer land, we didn't prove this third hour, but I'm proving it now, at least in this case. So you have negative 2 is equal to negative C1 plus C1 times I. Then this one's going to be a little nastier. 2 times negative 1 is negative 2, and then 2 times negative 2I plus C1 plus C1 times I. Now something should cancel. The negative 2's will cancel, and thank you. So you're going to get just 1 is equal to 2C1 times I minus 2I, right? Oh, 0. That's right. This is 0, not 1. Negative 2I, negative 2 plus 2 is 0. Oh, thank you. Yeah. I had myself worried there. 2C1I is equal to 2I. What cancels out? 2I. No way! So C1 equals 1. And what did I say C1 was equal to? Half of A0. And what's C2 going to be? 1. It's 2 minus 1, so that's going to be 1 as well. So for the complex situations, C1 equals C2 equals A0 over 2. And I'm not proving it. You could prove this with variables, but with this problem, super helpful, because now what you're going to do is you're going to go back to the beginning here. To simplify this, I'm going to erase all of this stuff, just so I have some space. And I'm going to go back to A of n is equal to 1 times lambda 1, negative 1 plus I to the n, plus 1 times negative 1 minus I to the n. We don't like to leave those i's in there. It's not super helpful, so we want to get rid of the i's. So what are we going to have to change this to? Sys form. And for those in the computer, there's gnashing of teeth and tears abounding right now in the audience, but we're getting over it. We're getting over it. Why me? So if you go back 1 up I, isn't this just negative 1 plus I right here? What angle is this to here? Sure you do. Sure you do. Yeah, this is pi over 4, and if we're starting here, this is just going to be 3 pi over 4, right? What is negative 1 negative I? Negative 1 minus I. Well, you know what? We're going to stick with that. Negative 3 pi over 4. I like that idea. I like it a lot. We do need a distance here, though. So on my triangle, this is 1 and this is 1. Actually, it's negative 1. And so what will this radius be? Square root of what? 2. So this negative 1 plus I is going to be square root of 2 cis 3 pi over 4. What's negative 1 minus I going to be? Square root of 2 cis negative 3 pi over 4. So far, so good? So I'm going to take this out. No biggie. We don't have to cry. Square root of 2 cis 3 pi over 4, square root of 2 cis negative 3 pi over 4. It's not done yet, but it's a lot better than it was. Okay? Still okay? Now, this is going to be 1 times square root of 2 to the n cis. Boy, I wish I had a way of taking a power, this cis thing, to the power. Anybody remember? 3 pi, log-like, yes, 3 pi n over 4. And this one is going to be square root of 2 to the n cis negative 3 pi n over 4. What could I factor out? Yep. And this is 2 to the 1/2 to the n, which we'll come back to. This is the cosine of 3 pi n over 4 plus I sine 3 pi n over 4. We factored this out, right? Plus cosine negative 3 pi n over 4 plus I sine negative 3 pi n over 4. You can do it. Okay. Someone give me some good news. Yeah, we're almost done. That's good news. But what do we know about sine negative theta?
Negative sine theta.
Yes, so we can change this one here to a negative, right? And then this, what happens to cosine negative theta? Still the same. So wonderful things are going to happen. Okay. So I think you just had enough. These two will cancel out. You did this last year, I know. We did this a bunch of times on an IB test. And then 2 to the n over 2. And how many of these cosine 3 pi n over 4s do we have? We have 2 cosine 3 pi n over 4s. Yep. And now this can be simplified. 2 to the n over 2 times 2 to the 1 cosine 3 pi n over 4. Now I want the record show this is 2 to the what power when we combine those? N over 2 plus what? 1 cosine 3 pi n over 4. Now there's no way that that's the right answer. Something that weird. Do you see any I's in it? No. So that's what it should be. Go to the answers. Number 5. And I want you to look at that answer right there. Read them and weep. That's right. That's something? Love that. That is a good problem. A little bit beyond what I probably would do on a test, but we have seen them show up on the further math test in the past. But they're doable. They're doable.
Wait, so if you for some reason stop at